SwayamPrabha. Digital India. Educated India.
Today we are going to discuss about heterogeneous nucleation, and I am going to take examples both from the liquid to solid and solid to solid transformations, just to show you that how we can deal such a kind of problems in a both physical as well as mathematical manner. As I have told you in the class in the last or previously also, that heterogeneous nucleation is more close to the practical problems. In the industry or even normal certification conditions, there is always the presence of impurities in the liquid or in the solid. Impurities can be just like an oxide or a surface or the mold wall, or it can be even some chemical inhomogenities or an defect structure like a dislocations or a boundary or an edge. So these are evidently present in all the systems. That is why nucleation will be predominantly heterogeneous type, because it is very easy to nucleate a parent new phase inside a parent phase when there is an impurity present. So just to give you some examples, that heterogeneous nucleation is basically preferential, means these nucleation events will happen on certain sets of particles which will offer better tendency for nucleation. And this is very evident in this picture, where you see there are only few places where the solid phase, which is shown like a pink color, is forming on this cube. They are not uniformly distributed. So in the literature, people normally think that when we have an impurity or a mold wall, the way nucleation can happen is what is known as a cap, spherical cap on a substrate. Okay, substrate means a oxide or an inclusion or a mold wall or anything. Okay, so first we are going to consider the case of a solid phase forming from a liquid, and this nucleation happens on a substrate. So I have marked here substrate as a symbol S, solid as a symbol C, liquid obviously will be as a symbol L. And here you see that substrate is known as a mold. It can be a mold wall or it can be a solid particles, oxide particles on the mold surface. So therefore the solid which is forming from the liquid is forming like a cap on these. Okay. And few important things before you get into the board to explain it in details, that the interfacial energies which are given as a solid liquid gamma, crystal liquid gamma LC, and the gamma CS, that is substrate and solid, substrate and crystal and solid and the substrate, they are actually meeting at the point at which this solid, newly formed solid, is touching the substrate, and at the meeting point these energies are balanced, and to balance it you need to have a contact angle, and that contact angle is given as a theta. Basically any heterogeneous nucleation, when something forms on a substrate, there has to be a contact, and the contact is defined by an angle. That angle is known as theta. So now if I go back to the board and just use the same methodology which I have used in the last class for the homogeneous nucleation and explain you. Okay, so I have derived some few mathematical formula in case I do not forget. That is why I am going to use these charts. So first of all, you see here that the model which I have used, it looks like this. If I have a substrate like that, okay, this is substrate, and we have a solid phase which is known as crystal forming out of the liquid. And as I said, interfacial energies are balanced at this point. 3 interfacial energies. This is gamma Cs, that is gamma Ls, liquid solid, and this is gamma Cl or Lc, liquid and the crystal which is formed. And this balance is basically leading to a contact angle theta. So what you see here, as you know, delta G has 2 parts. One is the volumetric part, other one is your surface energy related parts, which we can define as a interfacial part. That's better actually, because there are different types of surface energies here. So first let us calculate what is delta Gi. For calculation of delta Gi, that means the part, free energy part which is responsible for the interfaces, we need to look at this picture carefully. Initially the substrate was in contact with the liquid. So therefore the interface between substrate and liquid was present. And as soon as this crystal was nucleates on the substrate, this interface which was there initially between substrate and the liquid is now no longer present. So therefore this energy is recovered. The energy, surface energy, because of the substrate and the liquid which was there earlier, the formation of the solid nucleus has basically happened in such way that this energy which was there earlier was recovered, okay, or this energy is basically taken back by the system. On the other hand, 2 new surfaces are created. What are these? One is between the liquid and the crystal, other one is between the crystal and the substrate, right? So liquid and the crystals basically forming an interface along this curved surface, and solid and this substrate is forming an interface between along these things. So basically the earlier surface which was between substrate and the liquid is now replaced by the crystal and the substrate. So that means what? That means we can write down delta G is basically interfacial energy interfacial energy due to enucleation minus interfacial energy gain interfacial energy gain due to substrate. That's what is the gain because of the nucleation. So how we can write down that? That can be easily write down. This is the interfacial nucleation, is basically has 2 parts, one between crystal and liquid and the crystal and the substrate. So therefore the surface area between crystal and the liquid multiplied by interfacial energy between crystal and the liquid, that's the Lc, plus basically interfacial energy between crystal and the substrate multiplied by surface energy or interfacial energy between crystal and the substrate, that's the energy because of nucleation, minus the gain energy, that's again a Cs, the surface area remains same, multiplied by gamma substrate, liquid substrate. Okay, am I clear? That's the actually energy balance because of the nucleation of this new phase on the substrate. Now we can actually write down this very clearly, gamma ALC, gamma LC plus, okay, as you see here ACS is common, so I can take out that, so it becomes gamma CS minus gamma LS, right. So, and we can think of this one a little bit different way. I remove this now. We can think of this construction like this. We can think of this as a spherical cap of a larger sphere of radius r. Okay, you can always draw a larger sphere. Okay, I am just doing part of it. So that's the spherical cap of a larger sphere of radius r. Okay, now I can actually write down this as like this, ALC gamma LC. So ACS is what? ACS is this surface area, that's nothing but pi r square, if r is this one, gamma CS minus gamma LS. That's basically my delta GI. Alright. Now as I know, as I told you that these three interfacial energies, that is gamma LS, gamma LC and gamma CS, are actually balanced at this point. Both the vertical and horizontal components are balanced. Okay, if I simply consider the horizontal components, I can write down gamma gamma LS, this one is equal to gamma CS plus gamma LC cos theta. That's very clear because of the energy balance. You can see the cos component of these plus this one will be equal to the gamma LS at this point. Now I can actually use this expression to convert these terms, CS minus LS. Okay, so gamma CS minus gamma LS, gamma CS minus gamma LS is nothing but minus gamma LC cos theta. So if you plug in that into the delta GI will become SLC gamma LC minus pi r square cos theta gamma LC. So that's what is my interfacial energy term. Okay, we will see how to calculate surface area LC later. So that I can easily get converted. Now what about the delta GB part? Delta GB is a volume part. So therefore this must be the free energy multiplied by the volume of the spherical cap. So that's nothing but Vc, that is the volume of this crystal which is formed here, multiplied by these two terms, minus chemical energy plus strain energy, that we have seen earlier. So therefore total energy is delta GB plus delta GI, that's equal to Vc multiplied by minus delta C. I am intentionally making this one minus, in the books they have not given. It's obvious because the state energy is always a positive part and volume free energy, chemical free energy is basically it's a negative, that's why. But in case if you were to use both of them positive, the same sign, it's not going to create problem. Only when you are going to calculate the values, you will see the negative and positive signs in the picture. And delta GI is this, A LC gamma LC minus pi r square cos theta gamma LC. Okay, so that's what is basically my final equation. Now what I need to know? What I need to know from the geometric construction is the surface area between this crystal and the substrate. That's what is gamma LC. That's that's ALC, the crystal and the surface area between these two, between the crystal and the liquid, this surface area, the cap surface area, and the volume. Now geometrically this is done in the book, you don't need to do it, you can do it yourself also. The value of this one is simply this, I am not doing it because this is geometrically possible to do it, you should try. I have also tried and you can get it. Second is that LC, that's equal to basically twice pi r square 1 minus cos theta. Correct. Now once you put it everything there, you will get a delta G star. Okay, or basically this is, let us write down, this is heterogeneous, that's better because homogeneous one was delta G homogeneous. So therefore delta G heterogeneous is equal to basically it will be like 4/3 pi RQ GC plus GS plus 4 pi r square gamma LC multiplied by a factor twice minus 3 cos theta cos q theta by 4. It is better you do this math yourself. Okay. The final mass means from delta G heterogeneous by putting all these values and get this equation. So what do you get? You get that this is basically nothing but delta G homogeneous nucleation. So therefore the factor which is coming into picture when you do the calculation for heterogeneous nucleation is the 2 minus 3 cos theta plus cos q theta by 4. That is the main difference which makes heterogeneous nucleation so potentially important in the actual applications. That factor basically is nothing but related to the contact angle. So therefore you see this is nothing but a function of f theta, and we always in the books we write this as f theta because that is the factor which governs most of the heterogeneous nucleation aspects in the liquid and the solid also. So thus simple by using this CAB model which is very popular and which is basically energetically favorable model, we can actually get down into nucleation aspects. So one can actually do all kinds of things. You know that this is already related to R, so therefore R star can be calculated simply integrating this formula with respect to R, simply differentiating it. So that is nothing but by putting delta G heterogeneous by del R, make it 0, and you can then calculate delta G star heterogeneous, the barrier or the height of the barrier or height of the barrier height of the nucleation. That all these things can be easily calculated. Okay, that is part of very simple. This will be all coming into same. This will be equal to again twice gamma LC divided by this one minus GC plus GS, correct, and delta G heterogeneous also will be coming as a function of theta. Basically this will be coming exactly same as delta G star homogeneous and multiplied by f theta. So therefore you can clearly see the nucleation barrier is basically, I can again write down for your reference, so that the height of the barrier for the heterogeneous nucleation is basically a function of f theta when you compare with homogeneous nucleation. We will see all these things later part of it. Fine. So that is the important part of the mathematics which you need to know as a part of your discussions. Remember these functions we need to look at in details. So that is what we will do now. How this function looks like, and to do that let me just erase this part because that function is going to make the all difference of the homogeneous heterogeneous nucleation compared to homogeneous nucleation, that f theta, because f theta comes everywhere. The ratio of the heights of the barrier for nucleation as well as the in the total function of the phi energy. So let me just write down the values of f theta. I have calculated these from the book, okay, and take this thing. So f theta is 2 minus 3 cos theta plus cos q theta by 4. So these are the values of theta in degrees, and this is the value of f theta. Okay, and these are my comments which I will write down. So as you see here, when the angle is 0 degree, what is the meaning of 0 degree? That means it is a complete weighting. That means this solid C which is formed on the surface will be completely weighting the substrate. That is only possible when? That is only possible when, let us write down this expression, gamma Ls is equal to gamma Lc plus gamma Cs cos theta. The cos theta 1, theta 0 degree means cos theta equal to basically that means that theta equal to 0, cos theta is equal to 1, and that means gamma Ls is equal to gamma Lc plus gamma Cs. Analytically this is completely balanced. For that f theta value will be very small, basically it is 0.00017, that means no barrier is present. The barrier height is basically very small. Okay, you can see this is basically 10 to the power minus 4 times the homogeneous nucleation barrier, because this f theta multiplied by homogeneous nucleation will gives you barrier, will give you, provide you with the heterogeneous nucleation barrier. So if it is 10 degree, this is little bit higher. If it is 20 degrees, still a little bit higher, but quite a bit higher, sorry. And 50 is how much? 10 degrees, 50 degrees. No, this is actually 50. 90 degree is become 0.5. 90 degree theta means is basically like this. This is 90 degree. So that means what? There is a contact angle is going to be changing. 110 it will be 0.75. 150 that's equal to 0.99. 170 0.9988, and maximum angle perceiving is 180. 180 means what? It will be hanging on the like a point contract. If I draw it properly, 180 corresponding to is just like a, if you put a mercury on a glass, that's a 180 degree situation. Okay, that's basically point contract is equal to 1. So as you clearly see, this is no barrier. Barrier is same. When it is hanging on the substrate, the crystal is hanging on the substrate from the liquid. That means barrier for homogeneous heterogeneous nucleation is same. There is no difference. But when it is 0 degree, there is no barrier. So what I can tell? These are the situations of good heterogeneous nucleation. Okay, and these are actually bad heterogeneous nucleation situations. Worst will be one which theta is equal to 180 degrees. So simply by looking at the values of f theta, different values of theta, you can actually design the nucleating agents in the industry. As you know, when you want to, there are many examples which I'll discuss you in the, as the time goes by. First example of such a kind of situation is the seeding of rain, basically. You know, rain seeding is a very important thing in the many parts of the world where the amount of rain is basically small, and so if you want to seed rain, what people do is that they sprinkle silver halide crystals, either silver iodide or silver chloride crystals on the upper part of the atmosphere. And these silver halide crystals with the hexagonal crystal structure, they allow the rain droplets to form directly from the cloud. Idea is exactly same. To design a heterogeneous nucleating agent, you must try to make f theta to be as small as possible, because that's why the good heterogeneous nucleation thing will happen. That's why the barrier height delta G will be reduced substantially, and to do that you need to theta as small as possible. If it is 5 degrees, 2 degrees, even it is better. 10 degrees is not bad, it's basically 2.7 multiplied by 10 to the power minus 3 of times of the heterogeneous nucleation barrier, homogeneous nucleation barrier, that's not bad. But making it very close to 0, like 2 degrees or 5 degrees or even 7 degrees is also good. So this is what is used. Similar example of the, in the cloud seeding, similar example is basically using ferrosilicon in the steel casting, or the addition of ferrosilicon, or addition basically in cast and casting. Ferrosilicon, you know, is basically added in the cast iron to make nucleation happen, and they are actually known as inoculants in the real industry. People say inoculant. Inoculant is nothing but you put it in the mold so that they actually allow you to have many heterogeneous nucleation points in the solid. So the grain size can be controlled. Similarly, there are examples of, when you want to cast spiral graphite iron. Spiral graphite iron has the spherical separate graphite in an austenitic matrix, or it can be paletic matrix. But important aspect is to have large number of graphite, spherical graphite particles inside these materials. So to increase the graphite nucleation, people normally add into the melt synthetic graphite, okay, because graphite has a very high melting temperature, so they will never melt in the cast iron melt. Cast iron melts about 1200 to 1300 degrees Celsius temperature. So in that melt, if I add pure graphite, crystalline graphite particles, the graphite particles will act as a heterogeneous nucleation to nucleate graphite on graphite. And nucleating graphite on graphite, theta will be very small, because graphite will have a perfect match with the crystal which will be forming from the liquid. So therefore theta will be very low. Theta will be close to 1 actually in those cases. A little bit distortion in the surface possible because of the thermal because the temperature differences between the solid graphite which is forming on a graphite particles. So, and the barrier is very small. That means what, if I add synthetic graphite into the melt of ferrule graphite iron, what I am going to do is create a large number of heterogeneous nucleation sites, and so that the graphite size and size basically, and the number density in the sample can be increased. And that is what is important in spiral graphite iron. So in that way one can actually do the microcrystal engineering as a part of the phase transformation, and this is very natural way of doing things. Now next I am going to take examples of different type of heterogeneous nucleation event that you see on the screen. You can have, these are basically solid and solid. You can have this CAP model again in solid and solid, but equations will remain same, so I do not need to derive. Only thing it will change is this gamma values, gamma alpha p, gamma alpha beta, gamma p beta, because p is basically already present something, some substrate, a precipitate or whatever, and beta is the phase which is nucleating from the alpha. You can also have a nucleation at the grain boundaries, you can also have nucleation on the grain edges or grain corners. So we will see it how we can deal this kind of situation in the next lecture.